So good afternoon everybody. Today will be your first DSP lab class. We'll start with the design of analog Butterworth filter. So the aim was to design an analog Butterworth filter which has at -2 dB passband attenuation at a frequency of 20 radian per second and at least -10 dB stopband attenuation at 30 radian per second. So the parameters are being given this way, and the order is being calculated in this way. So to find the cutoff frequency omega c, there are two ways. One is using the passband parameters, or you can use the stopband parameters. We'll try to calculate it for both these values, and I'll show you the difference in the results. So in step 3, the transfer function, this is a standard transfer function. So you can write it either this way, or you can write it in terms of poles in this way. So in the third step, the transfer function of a filter is obtained by substituting S by omega c in equation 2 and 3. Since we have two values of omega c, we'll start with the first one, 21.3868. So instead of S, I'm substituting S by omega c value in the transfer function. So if we solve this, we'll get it someone of this form. Keep it. Or you can substitute that S by omega c in this equation. So this will become S by omega c square. So instead of S, substituted by omega c, which is this value. So again, solve it, you'll get it in this form, and then this you find the poles of this equation using that minus b plus minus root of b square minus 4ac divided by 2a. Using that, you will get these poles. Okay, so since it's a fourth order equation, so you'll have 4 poles, 1 2 3 and 4. Okay, keep this also. Okay, now similarly for the next one is at omega c is equal to 22.7951. again you substitute it under two forms of equation, okay, and solve it, and you'll get one this way and the other one is in this way. Okay, so keeping all these calculations in hand, I'll show you how to solve this in Matlab. Okay, so getting back to how are we going to represent these equations, how are we going to get these results in Matlab. First, in the Matlab editor, I'm initializing all the parameters. I'll call this as k1 and k2, omega p and omega s. For the simple reason, I don't like to write these special characters omega and alpha. That way I just interpret it into simple English alphabets of k1, k2, omega p and omega s. So in the program, I'll write k1 is equal to 2, k2 is equal to 10, omega p is equal to 20, omega s is equal to 30. So to calculate the order, when we calculate, we do it using the formula. But in Matlab, there is a function which gives you the n and omega c directly. So this function is called Buttord, B-U-T-T-O-R-D. This will give you the order and the cutoff frequency. So you enter the omega p, omega s, k1 and k2 and s. This is in single quote. S means it's analog. When you write S here, means it's analog. So after this, you write a semicolon. I didn't have space, so I didn't write. But after that, you write a semicolon there. So first you write the initialization, then you write this. You'll directly get n is equal to 4, and omega c, you'll see that time it'll give you this value. It will not give you the this passband parameters value. It'll give you the stopband parameters value. I'll show you why they choose this value. Okay. Now in Matlab, suppose you wanted to get this equation. Since for different order, the transfer function changes in a Butterworth filter. So suppose you forgot about the generalized equation. So what you do is, you write these two lines. ZPK means zeros, poles and gain. Use this function Buttard. N is the order of the filter. So you write Buttard N semicolon num and den. This is pole zeros to transfer function. use this function to get this numerator and denominator. It'll give you these values. It'll not give you in this form. Maybe it'll give you one this value. No, it'll give you in this form. 1 by S4 is equal to this one and this one and this one. Again, in this step, once we started calculating S by omega C, to get this equation, you have to use this one. B comma A is equal to butter because it's a Butterworth. So n omega C S. S means in the analog. And then the transfer function of B by A. So this transfer function will give you in this form directly. Okay. Again, if you want it in this form, use these two lines. If you want it in this form, in terms of poles form, you use butter n omega cs in forms of 0, poles and gains. Okay, so you'll get the zeros is these values, poles is these values, these poles, what these values are. So now this is a total program for your Butterworth filter analog. So till here I've taught you this is how to get the order and the cutoff frequency. This is how to get the transfer function for a particular order, and this is how to find the calculated function for the specified parameters, and this is how to get the transfer function in form of zeros and poles waveform. And this is how you plot. So when you do freqs, this is FREQS. When you put S here, which means you're trying to plot it in an analog domain. So B and A, for this transfer function B and A, it's going to be interpreted into S and omega. Into Y is equal to, we're doing this because we are plotting it against frequency versus gain. So in dB form. So we are going to multiply it by 20 log 10 of absolute value of H. So plot the W values and the Y. When you do plot means it's actually X, this will be X1 values, this will be the, this is the X axis, this will be the Y axis. Y limit means you're trying to constrain the limits of your Y axis. Grid on means your graph will have grids. This X label means label what is there in the X axis. Y label means label what is there in the Y axis. This is the title of your graph. Okay. So we'll continue with the Matlab. So your Matlab looks something like this. Okay, this is Matlab 2015 I'm using. This is where you write your program. This is called the Matlab editor. This is where you write your program. This is your command window. Your output generally comes here, and all your variables are being saved in this workspace. Whatever variable you have defined are being saved in this workspace. So I'll try to execute the program for you line by line so that you can see the difference. So initially, whatever variables I've told you in that problems, I've defined it like this. Okay, make sure you use this semicolon after everything. Semicolon means it's the end of a line. So even if you pile it up in one line, it's not a problem. But it shows that these are two different things by putting a semicolon. So by doing n omega c, it's equal to dot of omega p like this. Everything I showed you. So this is at the editor. Editor is there. Okay, from this tab there's an editor tab, and there's a button which called run. If I click this, okay, it runs like this. And then if you see in my workspace now, in my workspace, all my variables are there. Initially these variables were not there. So my k1, k2, my n is equal to 4, it's shown, and my omega c is equal to 22.7951, it's shown. Omega p and omega s is there. See this omega c, the cutoff frequency they're getting, it's from the stop band parameters. Okay, I'll show you later why they didn't take the pass band parameters. So now I'll delete line by line. So now to get the transfer function, because sometimes maybe you forgot what is a transfer function look like. So I'll uncomment this line and then I'll run it again. Okay, so my parameter, my workspace now will have this form. Okay, I've num and den. Okay, So my numerator is 1. Okay, in your transfer function, your numerator is 1, but since it's a fourth order, so you're getting 0. In the fifth one, you're going to get a 1 here. Okay, so I'll just close it down. Then num and den. In the denominator, you're supposed to get all the coefficients of your s, all the coefficients of s. So den is here, so I'll just double click there. I'll get C. My denominator is 2.6. These are the coefficients of the transfer function. Den means denominator, numerator, num means numerator. Okay, so this is how you get the transfer function in case you forget. Okay, so using these two functions, butter, enter the order, you'll get the standard, the general formula for a fourth order. So how do I find the transfer functions for the parameters? So what I do is, I'll just do for you this one. I'll just uncomment it. Okay, so now you'll get all this, all the transfer function which I've shown you. You please check this with your calculated values. Okay, so I'll run it again. So when I run it again, keep going back to your workspace and check. So now see your b is there. B is a numerator. Okay, so your numerator is 2.7 into e to power 5, that you also got. A is the numerator of your transfer function, the numerator. These are coefficients. These are coefficients. Okay, coefficients of your of s. Okay, of your transfer function. I'll just close them because I want to see the program. So now by using Fricks means you're trying to find out the analog values in of the transfer function. You already have the coefficients. You're trying to find out the analog values of it. So now the next is just plotting. Okay, so because I'll just uncomment this also. I'll just remove this, it's not a problem also. Okay, so next is after this is I wanted, since my y-axis has to be in dB, so I just multiplied it by 20 into log 10 into absolute of h. So I plot my omega and y values and my limit. This is my limits. Y limits means I'm trying to constrain my y so it doesn't go unlimited. I'm just constraining it into the value of minus 50 to 2. Grid on. I'll show you what grid on is. Sorry. And then this is my labeling the x-axis, labeling the y-axis, and this is the title of my graph. Okay. So after this, I'll run it again. So my graph looks like this. Okay. My graph looks like this. I'll show you. Where is your parameters? Your parameters is okay. So see here line by line, side by side rather. Okay, at k1 is equal to 2. K1 is actually the dB, the gain at 20 means at the passband values is at 2 and 20. So which means at 20 you're getting it around 2 because this is 0, so it will become 2 here. This is 5. Okay, at around 30 you're going to get 10 with omega s is equal to this is 30 radian per second and this is 10 dB. So at 30, sorry, where am I? Okay, so at 30, at omega s is equal to 30, you're supposed to get 10. These are the stop band values. K2 is a stop band value. So this at 10 you should at 30 you should get 10. So from the graph you're going to get at 30, you're going to get it at 10. Okay, 10 dB. Also at 20 you're going to get it around 2 dB. Okay, so this is frequency response, frequency response. You can change it, right, whatever you want. This is the you're labeling your x-axis, you're labeling your y-axis that way. Okay, so I'll just close up this one, and in the command window, you can see many things. See transfer function, it's coming. I've typed a transfer function also. This transfer function is equal to transfer function of b by a. It's coming this way. In the command window, you can see that transfer function is equal to like this. Okay, this is exactly the way you calculated it. Okay, hope this one is useful. In case you have any problems, any doubts, please let me know. Okay, I'll try to share the Matlab link with you later on. Thank you.